what is polynomial algebra, and denote by P usual polynomial ring over n variables over complex field, and LP is free left P model with generators. Well, so it is finite dimensional. Well, and our plan is to construct from it Lie algebra. So we need to define bilinear operation on these generators and variables, and we will do it by these formulas. So it's important here that our operation from variables is always equal to 0, and so it is defined by structure polynomials. Well, let's go further. Then it's not difficult to define our operation to expand it on entire LP with the Leibniz rule, as shown below. So here it's again important to notice that this term is always a 0, so we don't have any undefined multiplication of our generators. So we have defined bilinear operation on whole LP. Well, let's go further. It's easy to show that if we X our bilinear operation on generator, some generator, and any polynomial, then we will get something like this. So it's like a full derivative of this polynomial, but multiplied by our structure constants. Well, it's very easy to prove, I guess. We can derive this fact by induction, and then it's easy to see that we have this formula from which our statement follows. So we prove that this is true. Okay, let's go further. If I should stop somewhere, you can tell me.
Can I ask a question?
Yes, of course.
This brackets, it is operation on what set? On this model, or?
Yeah, it is operation on the model, but in model we have got 1.
Okay.
So we can multiply every polynomial by 1.
Okay, thank you.
Well,
maybe I will do some comments because you go so quickly and maybe the motivation is not clear. What is the year of publication of this paper?
Well, I don't clearly remember, but it's close to 2000, I guess.
No, can you check quickly?
Okay, one moment. 2002.
2002. Yeah. So because my idea was that it was earlier, but nevertheless, this is 20 years old. So this is not so recent, but this is very close to what we are doing now. So the idea is to study Lie algebra generated by some derivations. But now we want not to only to generate a Lie algebra by commutator of some derivations, but also we involve functions on which this derivation act. And we want to allow multiplication not only by elements of our field, but also by polynomials. And moreover, we try to have a free model. So let us go to the first slide. We consider some formal elements, L1 and so on, Ln, and add this unit. This unit represents somehow the ring of polynomial, which is inside of our model, inside of our algebra. And we want to organize a Lie algebra on this object to define this commutator. But the idea is, maybe go to the next slide here. No, the previous one, that this element Li, which is just a formal object, just a generator of this free model, this in fact acts on any polynomial like a derivation. So you have any derivation of a polynomial ring has this form, partial derivatives along variables multiplied by some polynomial. Here it is denoted by VIQ. So we have this collection of polynomials. This is written in this line, and we consider them formally as a basis of our free model. And now we will see how this idea develops, and so which class of algebra do we obtain this way. Okay, I don't know whether this comment helped to understand what happens, but nevertheless, I tried.
Yeah, probably I should say that every such polynomial Lie algebra is has a representation in Lie algebra of derivations. So maybe it's somehow describes the meaning. Okay, so as we are constructing Lie algebra, we need to demand from our operation to be antisymmetric and to satisfy Jacobi identity. So further formulas are really big, so we will use Einstein symbols. Well, antisymmetric is quite clear. I think no need to comment it. And Jacobi identity is very huge to write down, I suppose. But if we demand from arbitrary elements to satisfy it, we will obtain this equation for every index. So there is a big system of equations, and we need to demand it from, from this too. So it is main idea that if we want to construct Lie algebra, we need to demand from our structure polynomials such to satisfying such equations, first and two, and they will go with us throughout the paper. Well, it's important to keep it in memory. And so we have a definition here. If our matrix V and C, which is three-dimensional and V is two-dimensional, satisfies antisymmetric rule and first and second systems of equations, then these matrices define Lie algebra structure. So we will call such Lie algebras polynomial. Here is definition. Comes. Okay. Probably I'll go further and I'll give some examples and prove some general properties of such structure. Well, firstly, it's easy to show that if structure polynomials defines Lie algebra, then these structure polynomials are also okay. With it, they also satisfies first and two equations, first and two systems of equations. So with this fact, it's easy to find out which Lie algebras corresponds to constant parts of our structure polynomials. We can just direct alpha to 0 in this mapping, I guess. So here we have two cases. If V from 0 is 0 matrix and when V from 0 is not 0 matrix. Well, let's discuss the first case. If it's 0, then there exists such limit. Why is that? Because if it is 0 matrix, then we don't have any constant parts in our polynomials. So we just got linear parts and higher. So with this limit, we get either zero matrix or linear matrix. I hope it's clear. So we can set beta equals to 0, and we get two algebras, this one and this one. Okay. And the second case is when v from 0 is not equal to 0 matrix, then we just can set beta equals to alpha and again direct alpha to 0. And it's easy to see that we just get this polynomial Lie algebra. So there are three cases at all. Okay. And here comes some example. If all polynomials v are equal to 0, and polynomials c are constant, then in this case, algebra Lie contains n-dimensional Lie algebra over complex field with our generators. So it's quite not complex structure, I guess we get here. And from this example, it's easy to prove this lemma. If v from 0 is 0 and c from 0 is structure polynomials of some Lie algebra over C with some generators, then we can have such map, and this map is going to be homomorphism of Lie algebras. I hope the proof is trivial. Well, any questions, or should I continue? Okay. The second example, maybe it will be more familiar. Well, if we got structure polynomials v and they all are constant, and polynomials c all are equal to 0, so in this case, if we get back to system equations 1 and 2, we can see that arbitrary matrix v is satisfies our conditions. And the most important case is when v equals to identity matrix. We will get this polynomial Lie algebra, and it is clearly that it is isomorphic to Lie algebra of derivations over free P model with such generators, just partial derivatives. And it is defined by these equations. So it's clear that in our algebra, they are the same. Okay, if we denote our isomorphism by rho, then we have this. Okay, let's go further.
Maybe a short comment. This algebra, so what do we have in this case? We consider the algebra generated by polynomials and partial derivations. So this is sometimes called Weyl algebra. But Weyl algebra is considered as an associative algebra. And here we don't allow to consider products of partial derivatives. So this is the case of Weyl algebra. Here we consider only brackets. And so for brackets, we have only derivations of first order. And in this case, we have what we want, this polynomial Lie algebra, which is a free model over the ring of polynomials. And here we see examples of this structural constant. In this case, this matrix V is the identity matrix, and C is consisting totally of zeros. So this is quite natural example for this polynomial Lie algebras.
Okay, I'll go further then. Second example, more complex, I guess. If C are constant and they satisfy first system of equations, then such linear matrix is to be solution of equations 2. That means that with such structured polynomials, we can define Lie algebra. Well, it's easy to prove here. Basically, I provide all proofs because they're just straightforward and not difficult to understand, I guess. But there are a lot of indexes, so we just need to rewrite what do we have. And if we want this to be 0, it turns out that it is equal, that this formula equation is equal to 0. But this is just exactly the first system of equations, and by definition, we decided that C satisfies first system of equations. Therefore, it is correct. So this example is correct. Okay, let's go further. And now we have probably the most important lemma of this work, which describes why every polynomial algebra is does have a representation. Okay. If we've got such homomorphism of P models, mapping our generators to vector fields or just derivations by this formula. It turns out that this homomorphism is also a homomorphism of corresponding Lie algebras. And this representation is exact if and only if V is non-degenerate. Well, probably the second state is kind of obvious. Well, let's prove the first one, that it is homomorphism of corresponding Lie algebras. We need to check these equations, and it's again about indexes and rewriting things in other way. So I'm not sure I need to explain it, but yeah, the main idea is just to calculate everything, and we will find out that if we want this equality hold, then it is equal that this equation is right, and it is right by definition in our polynomial algebra. So this representation is homomorphism of Lie algebras if this system of equation holds. Well, I hope it's clear. Okay, let's go further, and I think I will skip it. It's just we need to check if this is also true, but it is very easy. So I think I should go further. Here I say that non-degeneracy of V is equivalent to linear independence of images of our generators. So it's clear that representation is exact if and only if V is non-degenerate. Okay, so now we can prove some corollary here.
And maybe again, just to, I don't know, just to make this presentation a little bit more funny, let us return to this lemma.
Okay.
To the previous one. Again, just a comment from the point of view which I want to stress here. So we took some concrete set of n, and on the one hand, n is a number of variables, and on the other hand, n is a number of these derivations, which we took, and we generate a Lie algebra and a model over the ring of polynomial by these derivations. And from the beginning, we decided to do more formal things. We construct formally a free model over the polynomial algebra and took these generators Li but we want these generators acts in the same way as our derivations which we took from the beginning. And this v, they are coefficients of these derivations. And now we consider very natural representation. We send formal object, this Li, to the derivations from which they come from. And it turns out that such a map is really a homomorphism, and even this is an isomorphism. So our formal object is isomorphic to this real object. But the second isomorphism turns out to be true under the additional conditions, and this matrix V of these coefficients is non-degenerate. So under these conditions, our formal object coincide with what we are going to study from the beginning. So model turns out to be really free, generated by these derivations. Okay.
I should continue. Well, as I said, we can prove this corollary. Okay, let's formulate it. Structure polynomials with constant matrix C, define Lie algebra structure if and only if. Structure polynomials C, define Lie algebras in n-dimensional vector space over complex numbers with generators L1 and so on. And matrix V defines representation, our Lie algebra to algebra of derivations by these formulas. Okay, how to prove it? First condition is just equivalent to antisymmetric condition and satisfying equations 1. And the second condition is equivalent to that we send our generators to these derivations. And for such mapping, we prove the equivalence of the following conditions, that this equality is right if and only if this equality is right. So we can change this condition to this condition. So it turns out it's true. Okay, so I'll go further, and now I will provide more complex example where matrix V is not linear. So define C by this formula and V by this formula, and V are quite hard here to understand, I guess, but it's coefficient by this degree in this polynomial, which is also defined. What do we need to check if this is a really polynomial Lie algebra? We need to check for satisfying first system of equations, well, here I prove it. I'm not sure it's interesting to discuss. We need to check if this equation holds, and it's true. It's easy to conclude, I guess. Further, we need to prove that equations 2 also holds, and for proving it, we need such properties of this sign, this one and this one. So how to prove it? Well, it's just a lot of indexes again here. Okay. Well, first property is that we can simplify this symbol to such sum, and the first one is we can get the rule of how to derive such symbol. So with these properties, it's easy to prove that system of equations to holds. We just need to rewrite our symbols in our definitions. So we'll get something like this. And clearly, this is equal to 0 because, well, we can just sum these terms and find out it. Well, so it is also polynomially algebra. Well, let's go further, I guess. Well, now we come to non-degenerative polynomially algebras and how to define it. Let delta be the determinant of matrix V. And polynomially algebra is called non-degenerate if this delta is not equal to 0. Well, and by representation lemma, we know that each non-degenerate polynomial algebra is isomorphic to Lie algebra of operators on P, generated by our vector fields images and operators of multiplying by variables. So further, we can write down system of equations to and it's easy to understand that this system of equations can have only one solution due to non-degeneracy of matrix V. Well, because we can again rewrite it if we represent it in this way. Okay, where right parts are defined here. Well, further, so yeah, we can conclude that symbol of our polynomial algebra from C and V can be simplified to just polynomial algebra from V, because we can find each C from this system of equations. Well, okay. And we have proved that if we have such isomorphy, that then system of equations 1 is right, holds, follows from system of equations 2. So to define polynomial algebra, we need only matrix V if it is non-degenerate. Well, okay.
So the conclusion is that the matrix C is not needed, right? It can be found automatically if we have this matrix V, right?
Yes, from this system of equations.
And maybe go to the beginning where this matrix appeared for the first time.
From to the very beginning.
To the very beginning.
Okay. Так. Так, сейчас. Не работает.
No, the first slide before this.
The first, okay.
So here we have definitions of C and V. Yes. So C, this is how to compute two derivations to our Li and Lg, and V, this is coefficients which are responsible for action of our derivations on variables. And so there is a simple explanation. Why don't we need matrix C? Because if we have V, then these derivations which correspond to symbols Li are defined, so we already have them. And if we know them, then we know how do they compute. So it's clear that we can compute coefficient C knowing coefficients V, right? Because V are coefficients of these derivations, and C are coefficients which appear as a result of their commutators. In the degenerate case, this is not clear. In fact, this is not true, because we cannot completely identify this Li with our derivations. This representation is not exact. This is not isomorphous. But in non-degenerate case, this is clear. So already from this definition, at least I believe that coefficients C are uniquely defined by coefficients V. Okay.
Now I need to get to the point again. Так. Well, we finished with this slide. Let's go further. So again, a simple example. If matrix V is diagonal and polynomial are not constant on the diagonal, then from system 2, we can get all C. And they are defined by this formula. And we need C to be polynomials. So we need to cross out this polynomial P in denominator. Okay, so this is a polynomial algebra only if all V polynomials are equal to some coefficients multiplied by the same polynomial Q. And the solution will be like this. So this is it. So if V is diagonal, then V must be constructed by only one polynomial. And only in this case, we will get polynomial algebra. So
again, I'm sorry, let me understand this in my terms. So the case which you consider now is that our derivations Li, they have the following form. Li equal partial derivative over xi multiplied by coefficient. So this is not a sum, this is just once a month. Li correspond to derivations over xi with some coefficient, right?
Yes.
So this means that this matrix is diagonal, right?
Yes.
And what I said before, certainly you can commute to such derivations, and you will find some coefficients of this commutator, which are these elements Cij. But when you commute to derivations, you obtain derivations with polynomial coefficients, but this is written in terms of partial derivatives. And the task is to represent this commutator in terms of these Li's. And this is not always possible in terms of with polynomial coefficients. You should divide by this coefficient pk, which appeared near each basis vector.
Mm-hmm.
And what you explain here, you explain what is the necessary and sufficient condition that this commutator of Li and Lj can be expressed as a sum of Li with polynomial coefficients. And the result is quite clear. This is quite predictable.
Okay.
Okay.
So then we'll get to our theory. Well, right part of system 4, again, system 4 is written here, can be represented in this way. So every polynomial on the right side is just this polynomials, and we can describe it in terms of our vector fields or derivations. So it can be simplified. And whole system 4 can be represented as such matrix equation. Well, I don't think it's clear immediately, but well, this is it. So we just write down our equation in other way. So we'll go further, and we denote by Cy matrix Cyjk, where G and K are changeable and Y is constant. Then, just as previous form, this form, we can represent Cy as a result of these matrix operations. So we just can compute our C constants, structure polynomials. And the question is when our Cy is actually a polynomials. Further, we can have a lemma, which can help us to derive the main fact of the presentation. Okay, let this C matrix be the solution of system of equations 2 for some matrix V, which is non-degenerative. Then the following equation holds. Okay. I'm not sure I need to prove it because it's just a lot of computations, but we can briefly look at this. So we just need to understand that this is a trace of this matrix, and trace can be simplified to this form, and at least we have identity in the second terms. Now we need to prove that trace of this matrix is equal to just vector field from logarithm from our determinant. Well, the definition is again just to compute everything here and write in another way. But eventually, yes, we can see that it is true. And should I describe it or what? Okay.
When you have some computations, it's good to comment what happens. Just to explain the meaning of this computation. What do we check?
Okay, the meaning of computations. We can simplify this formula to this sum. It's quite clear, I guess. And then we want to see what is this matrix is and what is trace of this matrix. In matrix vector field from V, an element with such indexes is equal to this sum. Then we need to multiply this matrix by V to the power of -1. And in this matrix, an element with indexes alpha beta is equal to this sum, so it's more difficult, I guess, and Vig and is algebraic complement. So that's how we compute determinant, I guess. So we can compute our trace, and it turns out that it simplifies to just partial derivative of determinant. So here we can have our proof that in this formula we simplified it to this sum, and in this formula we also managed to simplify it to the same thing. So our formula here is correct. Okay, what do we do next? So, and now we got the main theorem, which states that if we defines non-degenerate polynomial algebra, which means that a system of equations has polynomial solution, then all vector fields from determinant is divisible by determinant, where phi is some polynomial. And vector fields, here is a mistake, it must be y, along the hypersurface which annulate our determinant are tangent to this hypersurface. Okay, now I think it won't be complex to prove it because we can rewrite 7 and
maybe again a little break, because we need to think about this and to discuss this. Just, I'm sorry for this comment, but people quite rarely use in English formulation like основная теорема. So this is
yes, it's a mistake. Yes.
Secondly, what is y with index I? I forgot.
Y with index I is just the images of our generator, so it's derivations.
So this is the derivations which we start from, right? In my terms.
Yeah.
Okay. Now phi I is this, I don't know how to call it, eigenvalue, because this is this delta turns out to be an eigenvector for this operator, but this eigenvalue is not a number but some polynomials.
Okay.
And what is the sense of this theorem? So let us try to understand.
The sense of this theorem is that all our vector fields or derivations are tangent to a hypersurface which annulate our determinant. This is it.
Which annihilate our determinant, right?
Yes. More global sense, I am afraid I cannot provide, but with this theorem, we can further prove some little fact.
And this delta, this is determinant of V, right?
Yes, exactly.
So we took some collection of derivations. We construct a matrix of polynomial coefficients of these derivations. We suppose that this matrix is not degenerate, that the determinant is not 0. And then we see that this determinant turns out to be an eigenvector for these derivations. I don't know, some funny fact. So it's not clear, but nevertheless, this is true.
Yes, and it follows from the previous statement, really, from this one.
How to see that it follows?
How to see? Okay, did you have break? Can I continue?
Yes, no, my break is stopped. Now you can continue.
Okay.
Continue.
Well, actually, the second statement is following from the first, so the main idea is to prove the first one, and we can rewrite formula 7. Formula 7 is formula for trace, like this. If we can get back, we can see that we can get a derivative from logarithm. It just will be I from determinant over the determinant, and if we get this sum to another side, then we will just get this result. So I guess this is clear now that this statement holds.
Can you show one? Can you show one more time this lemma?
This one, yeah.
I don't see where. So you apply this derivation not to derivative, not to determinant, but to the logarithm of this.
Yeah, exactly.
And what is the connection with when you apply it to the determinant itself?
It's just not right. I guess this formula does not hold. What do you mean exactly?
But you have some formula which include the result of derivation of the logarithm of determinant.
Yes.
And how do you translate this formula in terms of action of this yi on the determinant itself?
Well, I'll try to write something down. As I understand, we can. Так, сейчас. Не могу разобраться, как здесь рисовать.
Try to speak English.
Okay. One moment, I want to try to draw. Okay. Well, as I understand, we can rewrite our formula in this way. So it's written down there only just for convenience. It should be written like this.
And then it's clear why do we have eigenvectors.
Yes.
I see. Then you just multiply, but this denominator, and you obtain a determinant on the right-hand side.
Yes, exactly. Well, okay. So it's clear that the first statement is true. Then the second one is easy to prove. We have this equation, and if we apply our vector field to determinant, then we get something like this, just from definition of our vector fields. So it's clear to see that if some point is belongs to our hypersurface, then we've got this equation. That means that our vector fields are tangent to our hypersurface by definition. So each vector is okay. I think I shouldn't say something. It's clear. Well, this is it. I guess it is the main theorem of my paper. And is it clear, or any questions? Okay. So
one more comment, because I try to understand. Let us take one derivation, y1, right?
y1.
This derivation has some coefficients, v. They form, I don't know, first column or first row of your matrix V, right?
Yes.
And then you take other derivation, y2, y3, and so on, yn. It's not necessary to write anything.
Okay. Okay.
And this other derivations, starting from the second up to the nth one, they don't know anything about the first one. They can be arbitrary. The only condition is that this matrix is non-degenerate, no more, right?
Yeah.
So only the first column of your matrix is responsible for the first derivation. And other columns, they are almost independent. The only condition is that it should be non-degenerate matrix.
Yes.
And then you compute the determinant of this matrix. And it turns out that it's an eigenvector for the first derivation, right? So this somehow funny thing. Only the first column knows about this first derivation, but the result, this determinant, is an eigenvector for this first derivation.
Yeah, exactly.
Okay, so this is just for me to realize what happens. Okay.
Okay. So now we have two examples in dimension 2. One, let V be non-degenerative matrix where I and J are can be equal to 1 and 2. So dimensional is 2 over ring P, again over two variables. So matrix V defines polynomial algebra if and only if these vector fields along the curve, I should remind probably this curve is contains of points where our determinant is equal to 0. So our matrix V defines polynomial algebra if and only if these vector fields along our curves are tangent. Well, it's easy to see. If we want to define Lie algebra over dimensional 2, we only need two structural polynomials because we have antisymmetric rule. And we can compute them from formula 7 for trace. From this formula for trace, we can find out that our structural polynomials C are just equal to this and this. And if we want them to be polynomials, not rational functions, then we need these terms to be polynomials also. Well, and this condition is equivalent to tangent condition. It's clear, I hope, again, because we can rewrite this one as y from determinant over determinant. So it will be again an eigenvalue of this derivation. So with this fact, we can prove that this matrix defines polynomial Lie algebra. Well, its determinant will be this function, and we have our vector fields from this formula. And these vector fields are tangent to our curve, because it's easy to see that if we just substitute our determinant into vector fields, that then we get this result, and that exactly means that these vector fields are tangent. So we can see that we define polynomial Lie algebra. That's just fun example, I guess, in dimension 2. So this is it, I suppose. Presentation is over.
So this theorem, which is the main theorem of this paper by Buchstaber and Leikin, at least in this presentation, it gives some systematic way to construct polynomial Lie algebras, right?
Not exactly, because in dimension 3 we cannot state the same.
But theorem is true in any dimension, right? So let us return to the formulation of the main.
Yeah, of course, the theorem is right for all dimension. Yes, of course.
Because theorem, this main theorem, the second statement, is the statement only in one direction. Such vector fields are tangent to our hypersurface, but the converse statement is not at least stated. And in this example, let us go to your example. You used that there is an equivalence, defines a polynomial Lie algebra if and only if this vector is of tangent. So this is some specific of dimension 2?
Yes, just because the dimension is very small, and we can write down all what we need in terms of formula 7, and in общий general, in other ways we can't write down the same, because not all structure polynomials C can be write down from the formula 7. This is it, if you understand me.
Dear colleagues, please tell something, because it's not clear whether you were present and whether you understand what happened. Is somebody brave enough to say something?
Very nice talk. At least I could follow a little bit. I think in dimension 2, in the example written below, I think it's easier to complete that matrix. Given X, maybe when there is X1, X2, X3 or something, is it easy to get those alpha betas?
Is it easier to get?
Easier, I mean, will there always a solution exist?
Don't understand the question. It depends on matrix V, or what do you mean? I get it. If we add some variables.
Yeah.
Well, by definition, as I understand, we can add as much variables as dimension of matrix V.
No, the question is, can you extend this example to dimension 3? So can you write down now the same matrix, but X1, X2, X3?
You mean?
Right. And Nikhilish, how do you propose to extend this matrix?
Yes, that is it possible to do it in
to find some
no, it's
constant
not possible. It's not possible because this statement is not right.
Yes. So
We can. Okay, continue.
So suppose my delta, I need a linear, I want my delta to be some linear combination of x1, x2, and x3. Some f1, x1, f2, x2, f3, x3.
What do you mean by you need it? Just in this case, we get the beautiful result, I guess.
No.
And in
Denis, maybe I understand. So let us consider 3 derivations. And all of them are linear. So they have some constant coefficients, right? Or
so here we write just alpha, beta, gamma, and
the question is whether you can find such something like this, right?
This case, you mean?
Which will satisfy all your other equations and conditions.
So we will get, I may be wrong, but we can compute our
delta you can compute, yeah.
It will be something like
the cofactor, yeah, which will be some beta 1 gamma 2 minus beta 2 gamma 1 times x1 plus something like that. Okay.
Some linear combinations whose coefficients are minors. And so this is 0 if and only if all minors are 0.
The problem is it's not very convenient to write something.
Yeah, I understand.
So yes, I can compute it, but it will be kind of.
But I think it's possible.
Okay.
Anyways, just out of curiosity, I asked, and nothing to bother you much.
Так.
Okay, difference. Some other comments, questions? If not, then let us thank Denis. Denis, am I right that this is your first talk?
Yes, you're exactly right.
And first talk in English, this is really difficult, I understand. But
kind of. Well, I'm afraid I can't erase this matrix because I don't know how to pick up eraser.
No, but this is very important matrix. It should not be erased. So this is with us forever. We will see this matrix for many years. So.
Okay.